Okay, so first of all, thanks to the organizers for setting this up. Thank you all for coming to my talk. I'm gonna tell you about the research that I did in collaboration with Luis Cortés Barbado from the University of Vienna. And we were looking at the Hawking radiation phenomenon as perceived by detectors in superposition of locations. So, first of all, Hawking radiation is a proposed thermal blackbody radiation released outside the black hole horizon. This is an effect of quantum nature because, as we know, classically nothing can escape the black hole horizon. And usually when we consider it, we think of a black hole that fixes the background, fixes the metric, some quantum field living in this metric, and a detector interacting with this quantum field, which we can find out that will click from time to time, testifying to the presence of some radiation. This surprising phenomenon is now well established theoretically. It is also deeply understood, which does not stop us from asking more interesting questions. In particular, based on the previous research of Luis and his colleagues, this time we ask what is the shape of the particles emitted by black holes. And what do I mean by that? We know that in quantum mechanics, particles are not well localized objects. Instead, they are rather blurred in space. This means that we can detect a particle by putting a detector here, but we can also shift the detector slightly to the left, slightly to the right, even here, and we can still absorb exactly the same particle. And now the idea of Luis and his collaborators was to put the detector in superposition. They were investigating the Unruh effect, the close relative of Hawking radiation, and they put the detector in a superposition of trajectories and argue that based on the final state of the detector, one can make conclusions about the spatial distribution of the particles. So what we do is we consider a Schwarzschild black hole, so a static, not charged black hole, a massless real scalar field living on the spacetime fixed by the black hole, and a particle detector that follows a superposition of static trajectories around this black hole, classical static trajectories. So more about the details of our problem. We have metric given by the well-known Schwarzschild metric. We have three kinds of dynamical degrees of freedom, which are the internal energy levels of the detector, the static trajectories that are followed by the detector, and states of the field. We assume that the interaction between the field and the detector is given by the standard monopole interaction Hamiltonian. So here we have a small coupling constant, a switching function which switches the detector on and off. We choose a switching function which has a Gaussian profile with a long time of interaction, a monopole moment operator, and a quantum field operator. We assume that the initial state of the whole system is given by the following formula. So this is the ground state of the detector, some state of the field, which will take to be either Unruh or Hartle-Hawking state, and a superposition of static classical trajectories. Now, we fix the beginning and let things happen. So we let the detector interact with the quantum field and look at the final state of the detector after the interaction with the field. We work in the first order perturbation theory, and final state of the detector is obtained by taking the final state of the whole system and tracing out field degrees of freedom. That's what we get. Slightly complicated expression, but I will just briefly explain what individual terms mean. So the first term is just the initial state of the detector. So it corresponds to the situation in which nothing happens, there is no excitation, nothing interesting. The second part is the sum over the diagonal terms with Planckian probability distribution, each with Hawking temperature. So this term is the sum of contributions from Hawking radiation effect to each trajectory separately, and these contributions are combined in an incoherent way. And finally, the most interesting part is the last line, which is the sum over the non-diagonal terms corresponding to the coherences left in the state of the detector after the interaction. So we find that in general, these coherences will be non-zero. And in this long expression, the really interesting part for us will be the coefficient lambda, which we take to be a measure of the coherence. And we find that this coefficient is given by such a formula. So this is just the normalized inner product between two states of the field, two different states of the field, left after excitation of the detector on two different trajectories to two different energy levels. Moreover, we find that lambda is zero unless this specific condition is satisfied. Here alpha n and alpha m are the gravitational time dilation factors on the trajectories n and m respectively. And this condition means that the energy of excitation as perceived by any static observer on two trajectories must be exactly the same. So why are we interested in this coefficient lambda? As I mentioned, this is an inner product between two different states of the field. If this is non-zero, it means that these two different states of the field are not fully distinguishable. So the situations where we absorb a particle on trajectory m and to some energy level and on trajectory n to some other energy level, these two situations are not fully distinguishable. And what can be the reason of such non-distinguishability? Well, they are not distinguishable because on two different trajectories we can in fact absorb the same particle. So in particular, if we fix one of these states, say this one on the right, this tells us on trajectory m we absorbed a particle to the energy level Ej. If we fix this state and require that this condition is satisfied, lambda will tell us what is the probability to detect the same particle on some different trajectory. And in such setting, lambda becomes a function of only two parameters. This is the radial distance of the other trajectory when we have one fixed, and the angle between these two trajectories. We have a spherical symmetry in the Schwarzschild spacetime, so there are only two parameters. And we can plot this lambda. So in fact, this is the shape of the particle if we take the initial state of the field to be the Hartle-Hawking state. So what we see is that we have a relatively sharp peak in the middle around the trajectory M. We have some small oscillations in the angular direction, some oscillations in the radial direction for r greater than r of the trajectory M, and we have a relatively large peak on the antipodes. So surprisingly, if we detect a particle on one side of the black hole, we have relatively high probability to detect the same particle on the other side of the horizon. Now, if we consider the Unruh state of the field as the initial state, we get this instead. So again, we have a peak in the middle corresponding to the trajectory M, and oscillations in the angular directions with a relatively large peak on the antipodes again. But now the peaks are extended in the radial direction. Is it strange? Well, not really, if we recall that Hartle-Hawking state corresponds to the thermal buff around the black hole, thermal buff of particles. So particles are swaying around some positions which are defined. While Unruh state is the state of outgoing flux of particles. So particles are going away from the black hole. So if you absorb a particle at some position, you can as well absorb it further away at the same angle from the black hole. And that's it if it comes to our results. There are, of course, many more interesting questions to ask. Some of them are written here, so one can try to do the same thing with other kinds of trajectories. So we did it for static trajectories on Schwarzschild spacetime, but one can try to consider detectors in superpositions of some other trajectories, some moving trajectories. One can also take a look on other spacetimes. So Schwarzschild spacetime corresponds to a neutral static black hole. One can see what happens if you consider a charged black hole, a rotating black hole. And finally, one can try to reinterpret our results in terms of quantum reference frames. So we view the situation as a black hole and a detector in superposition of trajectories. Within the quantum reference frame formalism, this should be equivalent to a particle with well-defined position and black hole in superposition of locations. That could be interesting to think of our results in these terms. That's it. Thank you.